That is something. Same procedure. Nothing, no other external change. So second example. So another B showing figure. This is suppose B and C settles down by 2000 psi and 1000 psi respectively. I will relatively simple example. Only concentrated loads. Loads may be changed anyway. Either UDL or eccentric concentrated load, or it may be triangle load, whatever it is. Only that fixed rate moment formula you have to remember. That's all. Other than that, there is nothing. So let us start. First step. Straight away we go down. I don't explain all the things. I will cut short. The local coordinates. So local coordinates means number and moments what we have to determine during analysis. This is the B, A, B, C. So I will choose the moments at the ends of the member as independent forces to be determined. Because shears I don't choose, only moments I will choose. Shear if I choose again, transformation matrix calculation I have to do. For that also, resolution becomes difficult, I will avoid it. Only moments because for local and global it is same axis, opposite axis. So I don't have to do it. That's the advantage. So I have to determine these moments at the ends of AB and BC. That moments to be determined, I will take clockwise only to start with. Some final answer, if I am getting a negative, that means we have to reverse this direction. That's all. So this is PM1, PM2, PM3, and PM4. These are the moments which I have to determine for the two members. If I determine this, shear also can be determined. I can draw shear force and that moment. That's the ultimate thing which gives moment of shear force at any point. That's as simple as that. So analysis is complete. So this is my local coordinates. So in the local coordinates, force which we have to determine are this PM1, PM2, PM3, PM4. It's a 4 by 1 matrix. This is what we have to determine. And global coordinates. Global coordinates are corresponding to kinematic indeterminacy. This is static indeterminacy. What the force to be determined, kinematic indeterminacy, what the displacement to be determined. So, the possible displacements are vertical and potential. Here, since it is fixed, both displacements are 0 as per boundary conditions. So here vertical is 0, here vertical is 0. And here this is possible, rotation is possible. So kinematic indeterminacy is 2. That's what you have. So this is the global coordinates 1 and 2. Local coordinates 1, 2, 3, 4. That's why it is 4 by 1. Here it is 2, it will be 2 by 1. So this is global coordinates. This is 2, 1. That is ds is a notation, global displacement to be determined. So that is 2 by 1 matrix. This is 2 by 1, this is 4 by 1. So your transformation matrix will be 4 by 2. You know, it is 4 by 2 each. And your stiffness matrix will be global stiffness matrix 2 by 2. Corresponding to that 2 coordinates 2 by 2. So all matrices you know. So other things are all only the mathematical operations of matrix. Addition, subtraction or inversion, whatever it is, that you have to generate and perform. So you yourself can write program for this and get this also generated. That's what syllabus says. You have to get that also done for complicated problems because they have put restriction, kinematic indeterminacy not more than 3. Here, next, second step, by the way, PMF, because all loads has to be at the joints, right? The fixed end moments, if I determine ABC, here you have concentrated load, fixed end moment, here it is anti-clockwise, here it is clockwise, WL by 8, that is 240 into 10 divided by 8. 240 into 10 divided by 8 means it is 300 minus. Here it is plus 300. Then it is 120 into L by 8 because it is also concentrated. So 120 into 10 by 8, that is 150. Yes. This is anti-clockwise, this is clockwise. Minus 150 plus 1. These are PMF. PMF is equal to minus 300, 300, minus 150 and plus 150 corresponding to these local coordinates. So therefore, your PS, that is load corresponding to the global coordinates, that is corresponding to this and this. Here it B and C. Here it is this and this sum. That is 300 minus 150. It is plus 150. So this PSC is nothing but PJ minus PMF. Minus PMF. These are all PMF. So it is plus 150 is the PMF. Minus 150 means it is minus 150. Here it is corresponding to D2. It is 150. That again reverse this sign. This is also. These are given load. Now comes this segment of support that to be added to this. Right? So because of segment, this is due to your regular load, not segment. Due to settlement. this same PS and this PS right now, I will keep it aside because I will calculate only for the given loading, then due to settlement, both I will add and then write the final PS for this. Okay? Because I have to add the load corresponding to given external load as well as load due to settlement. Settlement is corresponding to these degrees of freedom, which I have not considered at all. Mind it. Here, settlement means it is the vertical displacement corresponding to this one, restraint. Because of this is restrained, this settlement is not at all allowed. So it is restrained. But there is a settlement now. Because of that settlement, restrained movements are developed at the end. That restrained movements are also like this load movement due to load, whatever I have worked out, that you have to work out. Indirectly. Yes, you can consider in the development of stiffness matrix that vertical reaction also, and automatically it will take care. That can be done in finite element analysis. All vertical reaction, movement, everything. Then you can put the restraints. But here, shortcut procedure we are adopting. Only what is required and known, only we are taking. That's all the check, no other thing. Here, due to that, I will work out here. The settlement of support B settles down by 2000 by EI units, and this settles down by 1000 by EI. That means it has come down here, this has come down here. A, B, now B is here, C is here, E is here. Obviously, these are the things. So now, because of this, you assume it to be fixed. This is delta for member AB. Likewise, for member BC. This is that delta BC. This is delta BA. What is delta BC? Delta BA is nothing but 2000 by year. What is delta BC? It is the relative displacement we are talking about. So this is 2000 by EI, this is has come down by 1000. So the net displacement, relative one, is 2000 by EI minus 1000 by EI. So this will be 1000 by EI. This is important thing you have to take whenever there is a settlement. Otherwise, if they give only B settles down, then it is only 2000 by EI for both. Right? If I have one more span, that CD is not undergoing any displacement, forget it. But now that CD, one more span, is also undergoing 1000 by EI. That you have to take if you want more span is there. That clearly you have to take the corresponding this. So because of this, there will be a force here. There will be equal and opposite to keep it in equilibrium. This gives a moment in clockwise direction. So resisting moment should be, this is clockwise, resisting should be anti-clockwise. This you have to ascertain. So because to give a settlement, there must be a force in that direction of the settlement. That means like this. To keep this in equilibrium, equal and opposite force. So this force should be equal to this. This force is again is not in equilibrium. It gives a moment now in the clockwise direction. So this has to be resisted in anti-clockwise. So now this is in equilibrium, and this anti-clockwise moment is minus 6 delta by S square. This is what you have taken in slope deflection equation. rotation 4A by L, 2A by L, and translation, relative translation, sway. What I worked out earlier problem is non-sway. This is sway problem, but sway is not unknown, sway is known. Known sway in the case of beams, right? Otherwise, beams will not undergo any sway. It is non-sway. But settlement, if it is given, it is sway. Due to that sway is known, and due to that sway, we have to find what is the moment. That moment to be taken and added to the moment due to given load. That's all the change whenever there is settlement of support. Either settlement of support or in process, shortening of the member or temperature change, it results in expansion or contraction. That is settlement. Some movement. Due to that, you have to ascertain what is the force developed at the ends, and that force you have to add it to given global forces. That's all the only PS matrix or PS matrix will change whenever the secondary effects are occurring. The corresponding PS you have to calculate and add those corresponding secondary effects and proceed with the analysis. Otherwise, no other thing. Right? That's all you have to bear it in mind. Now this is what is the 60 I delta pi L square, that is 6 GI. Delta is settlement 2000 by EI. 2000 by EI. L square is 10 square, 100. So this EI will get cancelled. So you will get this minus 120. 6 into 20 minus 100. Here also it is same thing. So minus 120 because it is anti-clockwise both. The n moments are same direction. Now for this on same lines, you can work out. Only this you remember. 6 here delta by square. That's no deflection equation towards sway 6 here delta by square. That you have to take. So here this is like this. This equivalent opposite, it gives anti-clockwise moment. So here the moment should be clockwise. Mind it. Here it is clockwise. Here anti-clockwise. That's all the change. Correctly you have to work out due to the settlement what is the end forces. So here also this will be 6 GI. Delta is 1000 by year. That is I have written there. Delta of BC. It is 1000 by EI by L square. L square is also 10 square. So EI it cancels. You have 60 plus 60. So this is also plus 60. So due to settlement, I will add. This is due to load EMF, right? Due to settlement, here it is minus 120. Due to settlement, here it is again minus 120. Here it is plus 60. Plus 60. Here also plus 60. So your EMF here, that's all the change. Whenever settlement is there, due to settlement, you have to take what is the end moment. That's 60 and delta by S. That is sway. But sway is known. In frame problems, sway is also included. All the three we are taking into consideration, all the three degrees. Both sway and non-sway. That also is there as special one. First problem, which I learned, non-sway. Second problem is also a sway type, but sway is known. Settlement. But in frames, it is sway and non-sway both. Okay. Because since it is degrees of freedom 3, I will take a problem with all the three coming. So sway also I will consider that. That's a more generalized one. I will work on problem on frame. that completes all types of plane flame problems. So this net PMS due to load, due to swell, like that due to temperature change or any other shortening of members, all those things to be worked out added to only that PMS. So this is minus 420, this is 180, this is minus 90, this is 210. Therefore, PS equals, PS corresponds to D1 and D2. Here, due to D1, it is this plus this, MBA plus MBC. Correct? 180 minus 90, it is 90. That to be reversed. Sorry, minus PMS. So, this is minus 90. So, this is corresponding to D2, 210. That side to be reversed. So, it should be minus. This is the only change. This PS generation to be changed. Otherwise, it's all same. Only this step you have to be remembered. To the settlement, you have given now in the first step. And second step, stiffness. Element stiffness. Element stiffness matrix. KM. Element stiffness matrix. So you know already it's a real number. Km is given by 2E by I 2, 1, 1, 2. Standard stiffness, element stiffness matrix. So Km for the first element, second element. For first element, Km is 2EI. EI is constant here. It is 2EI divided by L is 10, 2, 1, 1, 2. So this is EI into 0.4, 0.2, 0.2, 0.4. So Km2 is equal to, again 2EI by 10, 2EI by L, 2, 1, 1, 2, plus again EI, 0.4, 0.2, 0.2, and 0.4. So therefore, the element structure stiffness matrix is equal to EI. For element 1, it is 0.4, 0.2, 0.2, 0.4. Others 0, 0, 0, 0. Here it is in 0.4, 0.2, 0.2. This is element stiffness. So this is for element 1, this is for element 2 along the diagram. Let's draw it will be. Next third step, transformation matrix. Transformation matrix. Or so it is very simple. So first, as usual, you have to give unit displacement along each of the global coordinates one at a time and calculate the corresponding local displacement, local coordinate displacement. So, two global coordinates corresponding to two global coordinates, d1 and d2 give unit displacement. d1 equals 1, d2 equals 1. Others you have to restrict. So here, as before, it will displace like that. This is the displacement. We have given right like that. Here. So here is 0, here is 0, here is 0, 0, 0. So your R will be corresponding to these member coordinates. So first 0, 1, 1, 0. Second 0, 0, 0. Same as previous one. Two displacements. Then fourth step, global stiffness matrix. AS, which is nothing but RT AM R, which I derived principle of contrariety. So therefore, KS is equal to RT 0, 1, 1, 0, 0, 0, 1, KM EI 0.4, 0.2, 0.3, 0.4, 0, 0, 0, 0, 0, 0, 0.4, 0.2, 0.4 multiplied by Km into R. R is 0, 1, 1, 0. So this is 4 by 4 matrix, 4 by 2, 2 by 4. So here this column equals row, resulting will be 4 by 2. Again this is 2 by 4. This 4 will go, resulting will be 2 by 2. This is DI into the 2 by 2 matrix. Point 8, point 2, point 2, point 4. That is KS. So fifth step, formation of equations. That is PS equals AS ds. That is your equation in that fashion. PS you have determined, that is combining the segment of support. So that is minus 90 minus 210. And that's okay. 90 minus 210 equals KS EI 0.8, 0.2, 0.2, 0.4 multiplied by D1. This you can solve or invert this and multiply by that. So that is your sixth step to find ds. That is unknown displacement. What is that to be determined? This and this you have to determine during analysis. Unknown displacement, unknown member and forces. This ds, you can find Ks inverse ds. Either invert this matrix, multiply by this ds. So solving this, you will get ds is equal to 1 over ei into 21.43 and 535 minus 535.71. This is that displacement you are going to get. Okay. And finally, remember last 7 steps. And 7 steps, what you have to follow. 6 steps after finding solution to find member and forces. That is the internal forces. So, you have this equation EM is equal to EMF plus this also to be added, that's all. Otherwise, you need not. EMF is Km into ds. This ds is nothing but or ds. Dm is or ds. So that is equal to EMF, here minus 420, that's including sentimental support. But if they give problem only load is separate, settlement separate, then you can take only this separately for settlement analysis. Otherwise, that's minus 420, 180, minus 90, 210, less Km. Km is EI 0.4, 0.2, 0.2, 0.4, 0, 0.4, 0.4, multiplied by R is 0, 1, 1, 0, 0, 0, 1 into ds. You have determined what ei into 21.43. This is minus 535.71. So ei cancels. So if you solve this matrix addition and multiplication, of course you check whether order is okay. This is 2 by 1, 4 by 2 into 2 by 1, it is 4 by 1 matrix, 4 by 1 by 4 by 4, it is 4 by 1, that is nothing but 4 by 1, you can add, they are of same order, so finally you will get this PM, which is nothing but PM1, PM2, PM3, PM4, that's the n moments, so that is given by final solution. I will give it, so you can verify it is minus 415.7, 188.6, minus 188.60. Naturally, final C support is simply supported, should not be any moment. MDL plus MDC has to be 0, so it has to be 6. So answer is. This is about the analysis of continuous beams due to sway and non-slip or segmental support like this. And one problem I can work for rigid plane frame that completes your unit 2, all the problems. So your last unit 5 also, by finite element same procedure. So same problems, only thing is I will generate only R and Ks. I will leave this. Only how to generate Km, R and Ks. Km, R, Ks. So that I will do by finite element procedure by taking global stiffness matrix straight away. The rest are all same. There are other matrices. They are all same. Formula for finding final moments and everything. Even data, that's also name change. First step. It is all common for both. You have to name the joints, name the members, mark the coordinate axis, and mark what is unknown to be determined. That has to be same. Whatever the procedure, classical or finite element, both it should be same. Only Km deflection, of course, that also has to be same. Which are the unknowns you will select? That's the only thing. Either shear end moment in case of beams at one end, or two moments you can select. Here I have taken two moments for classical approach because it is easier. The third axis it is same. That's it. There you can select anything. The two moments are all same. Here I will put the restriction straight away, make 0, reduce it straight away to stop it. There, reduction is done at the end after calculation of stiffness matrix in global coordinate. That's why I told you Km, Ks, transformation matrix. I will give the procedure. Yeah. Mainly the finite element method is applied mainly for determining the element properties by finite element approach. Element property. The element property we have to arrive at by defining displacement. First discretization, next defining shape functions for field variables, that is displacements, then find strain displacement relationship, then stress strain relationship, then generate stiffness matrix. So that process is done here in a shortcut procedure. That's all the change. So all that procedures I will explain in finite element method. What is discretization? What is element for the displacement model? What are the convergence criteria to be satisfied? And of course, degree of freedom selection and all same. Then how to formulate stiffness matrix, element property. That is how defining strain displacement matrix, constitutive matrix, stress strain relationship. So taking from elasticity, it's a definite procedure is there, step by step, wherein we can program it on a computer in an easy way. So that's why that method has been adopted. Easily it can be programmed. But here it is difficult to write program. Things are missing. Then you can write program suitably following the procedure. So that if I indicate the procedure, that's theory portion, 1 hour or 2 hours maximum. If I indicate the procedures involved, displacement model, how to discretize, how to number the nodes, all those things if I say property, then things will become very simple. That process also. Problems, same thing, same problems will work.